just a few, a selection. There's a whole list of graphs you can draw in Sage, so you can just go onto this week's Keats page and maybe find other graphs you can draw. So here's a very simple graph. Forget about references to chromatic numbers, we'll be doing that later. So it's called the house graph. Well, actually, the house graph probably wouldn't have the x in the middle, so this is the house x graph. Pretty simple, but you know, just get used to the sort of understanding the basics of graphs. The first thing you say to yourself, well, this graph has 5 vertices. Now, how many edges does it have? Well, it has 4 round the square, 2 diagonals. The important thing to notice here is that although these 2 edges cross, this cross is not a vertex. The vertices are obviously the big blobs. So a graph is a sort of combination of edges and vertices, but you need to mark the vertices clearly because some graphs you can't draw without crossings. Actually, this one we could just put the edge from 0 to 3. We just pull it out and put it round the outside. That would avoid any crossings, and this would be what's called a planar graph. So this is a planar graph, even though it's got a crossing in this representation. You can represent graphs, the abstract graph, in many different ways. So I was counting the edges. It has the square, that's 4, 2 diagonals, 6, 7, 8. It has 8 edges. And the other thing you should recognize are what are called the degrees. I'm going to write the definitions out in a moment. But there are the vertex degrees. Okay, so that means the number of edges that meet at each vertex. So here there's obviously just 2. Here we have 4, 4, 3, 3. And if you add up the vertex degrees, so it's 3 and 3 is 6, plus 8 is 14, there are 2, this has degree 2, so it's 16, and you divide that by 2 and you get the number of edges. Okay, because each edge contributes twice to a vertex degree, because each edge goes from one vertex to another, so it's going to count twice. If you just count the vertex degrees, you'll count each edge twice. So the sum of the vertex degrees of any graph has to be even, and it's twice the number of edges. That's a useful thing to know. Okay, well, you won't see this graph much in practice. You will see much more often these 2 famous graphs, because they form part of the theory. So the graph on the left is simply you have 5 vertices, and you have all possible edges. There's an edge for any pair of vertices, so that's why it's called a complete graph. It's a complete graph called K5. So each vertex has degree 4, so 4 5s are 20, so there must be 10 edges, which is correct. There are 10 edges, but it's a number of ways of choosing 2 from 5, because there's an edge between any 2 vertices. The other graph I drew right at the beginning of the course, this is think of it as the gas, electricity and water graph. You're trying to send gas, electricity and water at the top to 3 houses at the bottom, and you can't do this without at least one crossing. So here there are lots of crossings which are not vertices. There are only 6 vertices. Again, 6 3s are 18. That means there are 9 edges. This is what's called a bipartite graph, because what's going on here is that, in fact, there are 2 sets. There's the set of 3 at the top and the set of 3 at the bottom, and any vertex from the top set joins any vertex from the bottom set, but no 2 vertices in each subset are joined. So it's like it's a sort of complete in some sense. For this division of the vertices into 2 subsets, we've got all possible vertices from one subset to the other. So this graph is called K33, and these are sort of important. Neither of these graphs are planar. You can pull some edges out so that you avoid crossings, but you'll always have at least one crossing. If you want to draw these graphs in the plane, you'll have at least one crossing that's not a vertex. So again, we'll be talking about this later on, but these are examples of non-planar graphs. And in fact, there's a deeper theorem that says that if a graph can't be drawn in the plane without crossings, it must somehow contain either this or this in some hidden sense. So I like to think of these two graphs as sort of nasty in some sense. They're the germs that you would see in a graph that tells you can't draw the graph in a plane. So we'll come back to those. Another family of graphs is the graphs corresponding to the edges and vertices of a Platonic solid, in fact any solid for that matter, with straight edges and vertices and faces. So the 5 Platonic solids, which you should get to know, if you don't already, the tetrahedron, the cube, the octahedron. This doesn't look much like an octahedron, but if you think about it, the configuration of vertices and edges is exactly that of the octahedron, because the octahedron, you have a square and you have the sort of, it's a pyramid on top of a square, so that's 4 triangles, 4 triangular faces above and 4 below, and in fact this is full of triangular faces. Inside here we have 3, 4, 5, 6, 7, but then you have to think of the outside as one face. So this represents the octahedron, this represents the dodecahedron, which I have in my hand, which I showed you before, that has lots of pentagons. There's a pentagon at the top, and then there's a ring of pentagons, and then there's another ring of pentagons, and then it sits on the pentagon, which in this picture is really the outside of this, it's the outside face. And then this is I won't expect you to sort of construct this from memory. This is the icosahedron. Okay, so here we have actually 20 vertices, here we have 12 vertices. The cube, of course, you can do the cube in any dimensions. The cube, you can think of it as drawn in space, points in space in which you have Cartesian coordinates, 3 Cartesian coordinates, using just the numbers 0 and 1. So you have 8 vertices which correspond to the binary expansion up to 7. So there's going to be the origin 0, 0, 0. Then this point would typically be where the x-coordinate is 1, so this would be 1, 0, 0, 1, 1, 0, 0, 1, 0, and this would be 1, 1, 1. So if you think of that in space, then you can do a similar thing in 4 dimensions, or in any dimensions. You can think of a sort of cube in 4 dimensions, and that will also give you a graph, and you'll have, instead of 2 to the power 3, you'll have 2 to the power 4 vertices corresponding to the binary expansions up to 15. Well, from 0, 0, 0, 0 up to 1, 1, 1, 1, which is there. Which you can think of it as a sort of ordinary cube pulled out of itself into the 4th dimension. So a cube in the, and then all the edges joining the vertices. So you've got the 8 vertices, you've pulled it out of itself, you have 8 more vertices, and then you have vertices between any 2 vertices before. So that's that. And then let me just show you 2 other graphs, because I'm going to come to these probably today. Here is a graph with 10 vertices, and I'll explain how you can get that combinatorially. It's called the Peterson graph. Notice that this is an example of a regular graph, because all the vertices have degree 3. In fact, the other graphs were regular as well, the Platonic solids. But here we have a graph. All the vertices have degree 3. There are 10 of them, so there are 15 edges. Because 10 vertices, each has degree 3, so that's 30. Divided by 2 is 15. In fact, there are 15 edges, because there's an inner pentagram, there's an outer pentagon, and then there are the things joining. And finally, this is a bit more complicated, but it was quite important in the theory of graphs, because it has it has certain properties, but it has no 3 cycles. There are no, like the previous graph, there are no sort of triangles. The graph doesn't contain any triangles. That's the Grutch graph. That has 11 vertices. And there are different degrees. I'll probably write that out later. Okay, and then you can get incredibly complicated graphs. You know, if you play chess, you think of all the knights' moves. This is just the knight's move on a 5x5 board, let alone an 8x8 board, and you get all those vertices joined up in funny ways. Okay, let me go back to the notes. So a graph, what's the essence of a graph? Well, it's really just a configuration of points which are vertices and edges between those points. So it consists, copying from the notes, consists of. Now our graphs will be finite, so you could imagine an infinite array, but for this course all graphs will be finite. So there's going to be a finite set, which I typically call V of vertices. That means points, or there may be blobs, represented by blobs. And a finite set, well, a finite, I'm going to use this word family. I'll say why I'm not using the word set. E of pairs of vertices, which correspond to the edges. Remember, any edge, obviously, is something that joins two vertices. So, you know, if we want to define things without pictures, sort of make it all algebraic, we can say that a vertex, and of course, if you want to put graphs on a computer, you need some sort of algebraic scheme. So an edge is just a pair of vertices, basically. But I can't quite use the word set here, because there could be, let me give you an example. This is quite a well-known graph, sometimes called the Theta Graph, for obvious reasons, because it looks like the Greek letter theta. That's a graph. It has two vertices and three edges. So how would you describe that? Let's call the vertices u and v. That's not a problem. So v is the set consisting of little u and little v. There are two vertices. I'll often use n to denote the size of v, so it has two vertices. But what are the edges? Well, the point is, the edges really, the family of edges, I can't use, I mean, there are three edges. It's crucial that I write all three. So every edge goes from u to v, but it's sort of repeated three times, or repeated twice, so there are three of these things. So the family of edges is really the same symbol repeated three times to say that there are three edges from u to v. Obviously, you could also draw this with a big blob here and three lines like that. That would be another representation of the graph. But I can't write E is equal to set, open set bracket uv, 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 because according to the rule of sets, that would be the same set as single element uv, because a set is unordered. Okay, and that's logically wrong. So I can't do that. There's a similar problem with linear algebra, actually. I mean, I don't know, you know, if you think of a base, so just think a moment about linear algebra. You talk about bases. I don't know how you learnt this, but I mean, if I take the set here of two vectors in a vector space or in R3, let's call one vector v, suppose it's not 0. Underline it, show it's a vector. And let me take another vector 2v. And if I ask you, is this set of vectors linearly independent? What's the answer? It's not, right? Because one's a multiple of the other. So this set is not a set of linearly independent vectors. If I ask the same question for this set, what would you say? Is that a set of linearly independent vectors? Well, it's not clear. The answer is really no, because that as a set, as an unordered set, is just a single element, and that's linearly independent. Okay, so you see there's a bit of a problem, even in linear algebra with this. That's really why, in some sense, bases ought to be ordered sets. In fact, when you write a basis, you might use an unordered set, but write the basis as E1 up to En, but you are, in fact, thinking of it as an ordered set of vectors because you've labelled it 1 up to n, so there's an order here. So there's a sort of ambiguity already in other areas of maths, but here we have to be careful if we have, here these are called multiple edges. Sometimes we consider graphs that have no multiple edges. In that case there's no ambiguity, but with multiple edges you have this problem. You could also have a loop. You could have a single, you could have a graph maybe looking like this, but you could have a loop at one vertex. That's allowed in graph theory. Okay, so here if we call the vertices u, v and w, then the edges, the edge family, if you like, I write it as a sort of ordered set, would be uu, uv, uw, or wu, it's the same thing. And again, this shows you, I can't really write uu because I really want to see the vertex twice. That would be, if it was unordered, it would sort of go down to one element, and that's not ideal. So just, in practice, it shouldn't give you any difficulty, but just be aware if you want to be too rigorous, you'll make a mistake here. Okay, but we can get rid of this by restricting to simple graphs. Simple graphs have no multiple edges. That's not more than one edge between two vertices, and they have no loops. I don't want to always make that restriction, but often one does. So there's this definition of a simple graph. So a graph is simple if there are no multiple edges. That means more than one edge between any given two vertices, and no loops. So a loop is an edge going from one vertex back to the same vertex. But that's pretty restrictive because, for example, another famous graph is the figure of 8. And you do really want to, you might want to say something about this in other areas of mathematics. It's an important object. And, of course, this has two loops. So if this vertex is called u, the vertex set is just u, one element, but the edge family consists of two loops, u to u and u to u. A simple graph, it may as well write it, this triangle, that's an example of a graph, it's a very important graph, it's called a 3-cycle. So this is a simple graph, and it's the vertex set, 3 vertices, the edge set. Now I can use curly brackets because it's a simple graph, so I just have, strictly speaking, an edge would be an unordered set of vertices. So if I was really being very pedantic, I would say the first edge is the unordered set u to v, the second edge is v to w, and the third edge is the unordered set w to u. But obviously, you don't want to waste all that. It's laborious. So in practice, I just write this as, I can write it still as an unordered set, but at least on the inside, I just say uv, vw, wu or uw. Even though there's an implied order here, the order at this point doesn't matter unless I consider what are called digraphs, in which case I can put arrows on edges. So you can also consider things called digraphs, and if I consider digraphs, notation would imply I've got an arrow going from U to V, an arrow going from V to W, and an arrow going from U to W. But for the moment, our graphs will not have arrows. But with arrows, it's called a digraph, or directed graph. But as an ordinary graph, better write it again without the arrows, this is also called a three-cycle. In fact, it's the graph, this is the graph, what's called the complete graph on three vertices. So before I showed you K5, this is K3. Okay, because I've got three vertices and I've got all the edges between any pairs of vertices. Of course, I've got three vertices. If I choose 2 from 3, that's of course 3, and so I just have to leave one out. So that's why there are 3 edges. It's also called a three-cycle, so also called a three-cycle. And you can write it round a circle if you prefer. This is exactly the same graph. You don't have, it doesn't matter whether things are curved or not. That's the same graph. These graphs are what are called isomorphic. They obviously represent the same object mathematically because we don't really care how the edges are drawn. So at this point we can go in 2 directions. I can tell you what K4 is. So here's a picture of K4 in which we have 4 vertices. You've seen this before today. There are 4 vertices, and any pair of vertices has been drawn. So this is K4. Because here we have 4 vertices, we choose 2 from 4. There are 6 ways of doing that, so there are 6 edges. Okay, why did you see that before? Tetrahedron. If you look down from top, it's a tetrahedron. So it's also the tetrahedral graph. There are different ways of writing this. So you can also write it like this, or represent it like this, if you don't mind crossings. If I just take a square, as we've seen this before in the house graph, just take a square with its 2 diagonals. That's the same graph, as long as you understand that this crossing here is not a vertex. So these 2 graphs are what are called isomorphic. So these 2 graphs, isomorphic, they represent the same graph really, same underlying abstract graph. The structure is the same. In fact, these are completely symmetric. To make sure they're isomorphic, you have to do a correspondence between the vertices. It doesn't really matter doesn't matter how I order it, and put 1 down here, 2, 3, 4, because any 2 vertices are joined by an edge, there's complete symmetry. So I could just map vertex 1 to vertex 1, vertex 2 to vertex 2, and I'd be mapping edges to edges. It's a bijective map between the vertices which respects the edge connections. Again, I'll write that out properly later. Okay, well, I was saying I could go in 2 directions. So I started with K3 and I gave you K4, and then we also had K5 on the screen. Okay, but I could start with these graphs here of points around a circle. They're obviously simpler graphs, they have less edges. But let me give you the notation for those. Well, first of all, let me tell you what Kn is. I didn't already guess that. I'm just going through some standard graphs. So Kn would be when you write Kn, this would be, this notation stands for the so-called complete graph on K vertices. N vertices. So that means we have n vertices, 1 edge for each pair of vertices. Each pair distinct because it's a simple graph. no loops. So what does that mean? It means it has n choose 2 edges. So the size of the set of edges is n choose 2. And once n is bigger than 5, it becomes a bit of a pain to draw because there are lots of edges. You know, if n were 10, well, if n were 8, there would be 28 edges. So example, if n is 10, then you have 10 choose 2. What's that? That's 10 times 9 over 1 times 2. That's 45 edges. Cn stands for the cycle graph, the n cycle. Well, I just call it the cycle graph. I should think of a bicycle. N points around a circle, or n points, the vertices of a polygon with n sides. Let's say polygon with n sides. Or n points around a circle, as you prefer. Okay, so here's a 5 cycle. 1, 2, 3, 4, 5. That's C5. Or if you prefer, draw a pentagon. That's also C5. There's another graph, while we're doing this list, but there's also another graph if you put a vertex in the middle and join all the vertices around the edge to that central vertex, this is a different graph, obviously. It's called the wheel graph, and I would call this W6 because it has 6 vertices. You might prefer to draw a circle if you want to think of it as a wheel that's going to roll. I think some people might call this W5 because there are 5 around the outside, but I think I call it W6. Be careful here, I mean these are very different. So W6 has 5 vertices of degree 3 and 1 vertex of degree 5.